All right. Thank you all for being here. Thank you for inviting me. So my name is Chris Zangmeister. I work at NIST. I'm just a small part of this project. Most of the work that I'll be describing was done by Jimmy Radney, who is a postdoc at NIST. And also Rian Yu. She's a graduate student at the University of Maryland who works under Mike Zachariah's group, who's in the Department of Chemistry at the University of Maryland, which is very close to NIST. And Keith Gillis, who is a photoacoustic he's an engineer, he's a physicist, and he's designed many of the photoacoustic spectrometer, or at least the resonator that I'll talk about. So we've designed this new technique that we're calling supercontinuum photoacoustic spectroscopy, and it's part of a bigger project at NIST. And I'll just give you a general goal of that. So at NIST, we develop standards, and one of the things that we at NIST and other national metrology institutes, those are NMIs, are aware of is that we don't have any products for this whole area of science. And so that's something that we're trying to address in the next decade or so. And there's been international meetings in the last several months trying to address this need. And that's something at NIST that we're trying to work on. So I would say at NIST, 3/4 of what we do on this project is to try to develop aerosols with known reproducible properties. And that's sort of a materials characterization or a nanoscale manufacturing issue. And so that's the bigger part. So we're trying to address this existing gap, which is try to develop standards. So that's part of NIST and other research, other NMIs around the world as well. We also at NIST do a lot of development of new techniques, and that's what I'll discuss today, which is a smaller part of this overall project, but it's developing spectroscopic tools for understanding aerosol optical properties. And that's part of that is this photoacoustic spectroscopy. So typically in the world of photoacoustics, most people make single wavelength measurements, and it's difficult to have intercomparison when everyone has a different laser and is measuring different absorption cross sections. And so we're trying to develop multi-wavelength spectroscopy for aerosol measurements. And so that's what I'm going to describe today. So how do we do this measurement? Well, it's important to note that we do all of our measurements in the laboratory, and we mobility select and mass select, and that gets rid of a lot of issues with result to multiple charge particles, okay? And we have humidity control as well. So we have a couple of papers published on how we do this separation and trying to understand that. And then we have a couple of different types of spectrometers. We have a photoacoustic spectrometer that I'll describe in the remainder of this talk. And we also have cavity ring down spectrometers. And some of this work has been done at NIST for really a few decades for gas phase metrology work for gas standards. And we've just sort of leveraged off of that for aerosol work. And there are some papers here as well that describe some of the work we've done for photoacoustics. So photoacoustic spectroscopy, if you're not aware of, it doesn't matter if it's for an aerosol or for gas. It involves light absorption, that energy is converted to heat. And then you can have relaxation, which creates a pressure wave throughout the back gas that we can detect as sound using a microphone. And the heart of any photoacoustic spectrometer is shown here, this acoustic resonator. Okay, so our aerosol flows into this acoustic resonator, flows out. We have a laser that passes through that. You can kind of think of this as a drum that has a resonant frequency. And so at that resonant frequency, we chop our laser at that resonant frequency. And so we're beating at that resonant frequency. And we detect the sound with just a simple microphone, just a $5 microphone that we can amplify, and then we can back out the signal that way. Like I said, most people use a very powerful single wavelength laser. In photoacoustic spectroscopy, the more powerful your laser is, the more signal you have. And so that's why most people have single wavelength measurements. We've used this new type of laser system, which is a supercontinuum source. And the way that works is it's a white light generated source. It's a pulse source. It's fiber optically coupled to our system that we mechanically chop at this resonant frequency. And so what we can do is we have this white light generator, okay, and it goes from about 480 nanometers to just over 2 microns into the near IR. And what's nice about that is we can select a small piece of that light to inject into our system. And the trade-off to that is that we don't have very much power. We only have 2 to 4 milliwatts per nanometer. So that's a couple of orders of magnitude below what most solid-state lasers that people use for photoacoustics. So that's sort of the drawback to this. We have to we have to get kind of a large bandwidth, 10 to 20 nanometers of bandwidth into our system to get high enough sensitivity. So that's our trade-off, is low limit of detection or high limit of detection for spectral coverage. So this is one aspect of the supercontinuum source. We have this broad bandwidth system that we can select parts of the spectrum of with a tunable bandwidth filter, and so that's one nice aspect of that. The other thing that we didn't think too much about after we actually had our supercontinuum source is that we're modulating at this resonant frequency of our system, but it's also a pulse source, and this system pulses at about a half a nanosecond pulses. So we have half a nanosecond pulses within our modulation, and we'll try to take advantage of that. So I'll talk first about what we can do with the spectroscopic aspect or the wide bandwidth aspect. In the second part, I'll talk about what we can do with the fast pulses. Oh, so this is a very small system. This is a 3-foot little optical breadboard by 2 feet. This is the photoacoustic resonator here. This is the microphone here. It's a turnkey system that you can purchase. It's fiber optically coupled into a collimator. This is the chopper. This is our other extinction spectrometer as well. So we can do those two simultaneously. The first thing that we looked at was water vapor spectra, not an aerosol. It's a very simple experiment for us to do. We can just pipe through water vapor as a function, or just change the relative humidity of our system. These are 2 bands of the near IR, just 2 peaks, and then we can fit those to the HITRAN database, and we can see that we have quantitative measurements with the photoacoustic spectrometer. And these are 2 sigma here. And so we were pretty pleased with that. We can ramp the humidity over the course of a couple of days and follow the intensity of both of these bands, and we see that we have a very stable system. So that was the first thing we looked at. Anyone that's looked at photoacoustic spectroscopy of aerosol, everyone has to look at this material. This is called nigrosin. Everyone thinks of it as a black carbon material. It's really an organic dye that people use to stain cells, but it's a very black material. And then what I have here is this is the mass absorption cross-section as a function of wavelength of this nigrosin material. And this is what it looks like in solution, the black line here. And then since we can mobility diameter and mass select, we can measure the mass absorption cross-section as a function of aerosol size. And so this is 250 nanometer nigrosin here, and then there's 450 nanometer here. So you can see that we can see spectral changes as a function of mobility diameter, which I think this is the first data that shows that. It's been predicted by me theory. These lines here are me theory. We're a little bit off here due to we only use a single value for the real refractive index. But anyway, we were pretty happy that we could actually see size dependence changes using this new technique. So we can do other things as well. We can co-atomize this should be black carbon with ammonium sulfate. So this is the absorption cross section as a function of wavelength here. This is black carbon. This is just a material that we get from Cabot Corporation that's used for inkjet printing. And so it looks very similar. If you do the TEM, it looks very similar to collapsed soot. And so we can measure that. Then what we did is we co-atomized that, measure at 250 nanometers with a 10% mixing ratio with ammonium sulfate, and we can measure the enhancement. This is done by Rhian Yu at the University of Maryland in our lab. And then she's modeled different amounts, trying to model to understand how much of the material is inside the ammonium sulfate and how much is outside. And she has some TEM that shows much of the material is actually contained on sort of half in and half out of the particle. Same thing for sodium chloride. Most of the material sits outside the particle for sodium chloride, so we can see spectral differences there too. So there's 2 things. There's enhancement differences, and there's slight differences in shape as well. There's been some talk here about brown carbon, so we've looked at brown carbon as well. So this is the black carbon contribution. This is brown carbon. Again, it has that sort of slope that goes up towards the UV. We can only go out to 400 and 500 nanometers or so, but it continues to go on up. This open circle here is if we just take the co-addition of these 2 data sets, this is what we would expect. And then I'm sorry, this pointer is running out, but this is what we actually measure. So you can see there's a slight enhancement. Actually, there's a I don't know, 20% enhancement, 15% enhancement that we measure when we have this material, the two materials co-mixed together. So that's one of the neat things that we can do. So the last 3 or 4 spectra I just showed we can do if we just vary wavelength. Okay, now I want to talk about one of the pitfalls of photoacoustic spectroscopy, and that is the issue of coated particles. And so what happens if you have a coated particle with photoacoustic spectroscopy? When you put light into the particle, you can have light absorption, then you can have vaporization of the coated material. And so what that does is, instead of creating a pressure that you can detect with your microphone, that attenuates your signal because you have vaporization of your particle. So, I mean, this is well known in the literature, and people have actually measured enhancements with photoacoustics of materials that are non-volatile, sulfuric acid, DOS, DOP, very non-volatile, goopy sort of coatings. But for volatile systems, that hasn't been shown yet. So we thought we could use this supercontinuum source. We have a very fast laser pulse duration. That if you can imagine a system that has a small monomer like soot. If your pulse duration is faster than your heat transfer and vaporization rate, then you can potentially measure enhancements associated with volatile materials. So that's what we started to look at. This is our most recent data. So this is at a single wavelength. This is 660. This is a mass absorption cross section. In this case, this is relative humidity. And so there are 3 experiments shown here. This is sort of the classic experiment. This is instead of having a pulse source, this is a continuous source with high power. HP stands for high power. This is 150 nanometers. And you can see there's a slight slope, a slight enhancement as you increase humidity, but not very much. Then what we did is we took the same laser system at 660, attenuated it down to about 15 milliwatts, and you can see that we have a slight enhancement, but not so much. And then if we take that same amount of power, but we have the pulse system, we see quite an enhancement, almost a factor of 2. So we can, with this supercontinuum source, because it's pulsed, we think that we can capture these effects of volatile systems. And that's something we want to explore more of here in the near future. So this is at a single wavelength. This is at 660, parked right here. We can also do the same experiment where if we scan through in wavelength space. So this is ethylene soot, black carbon, or ethylene soot at 5% relative humidity. We do the same thing. We just increase relative humidity in our system. We see these 2 peaks I showed you in the first spectra. These are the water peaks. And then we can subtract off the 65% difference in there, and we can then get this in terms of mass absorption cross-section. This is 5%, and then this is at 70%. So we can see the enhancement difference between soot spectrally, see spectral changes, and capture that enhancement as well. So to wrap up, the advantages of this new technique is it's a turnkey system. You can just buy a supercontinuum source now, very wide spectral coverage and investigate coatings. The real challenge here is that what I didn't describe is that it takes 2 to 3 hours to generate each spectrum. In terms of being able to do that, that's a real challenge because you have to have aerosol stability. So being able to control your aerosol over that time range is key, and that's a real challenge. And the low laser powers, as I described earlier. The other thing is chromatic aberration. So when we're dealing with a very broad bandwidth source, so we're trying to focus light into a very narrow system over a wide bandwidth range, and that can be very difficult. So what we're moving on, and hopefully in the next year or so, we're trying to develop this new Fourier transform system where we can take all of that white light and put it through our system at the same time, and that will give us hopefully quite a bit of a multiplexing advantage, and that will give us hopefully a very fast temporal resolution that you can imagine putting this out into the field and collecting the spectrum in the course of just several minutes or so. So that's what we're hoping to do, and then we'll also have a much higher resolution. So you can imagine collecting gas phase spectra on top of this aerosol spectrum across the visible and the near IR. So that's where we're going. So anyway, thank you very much, and I'll be happy to talk after if you like.